Hi class, welcome back. Module 8, Lesson 2, more Wilcoxon tests. You see, in the last lesson, we discussed the Wilcoxon Signed Test. Generally, this test has less power than the t-test, as the magnitudes of the pairwise differences are ignored. This test only used the signs of the differences. And this is really why it was called the Wilcoxon Signed Test. Now, today in Lesson 2, we learned two new Wilcoxon tests, the Wilcoxon Signed-Rank Test. This is when we have paired data. We will also learn the Wilcoxon Rank-Sum Test. This is when we have unpaired data. Well, before I get into both of these tests in our short lecture, let me mention the objectives of this lesson. Number 1, select and conduct the Wilcoxon Signed-Rank Test and the Wilcoxon Rank-Sum Test. And number 2, program permutation tests in R. We did some of this in the last lesson, and we will do more in this lesson. All right. For the Wilcoxon Signed-Rank Test, this is a second nonparametric alternative to the paired two-sample t-test. As in the last lesson, suppose we have this random sample of pairwise differences. D1 is x1 minus y1, D2, x2 minus y2, out to Dn, which is xn minus yn. Here, x1 through xn is some random sample, and y1 through yn is another random sample, same size. Then, well, there were two different ways to say our null hypothesis. One way was that the probability that x minus y is positive equals 1/2. This was equivalent to saying that m sub d is 0. Recall that m sub d is the median of the differences, pairwise differences. Now, the way I've listed it, I've listed a two-sided alternative hypothesis in each case. Okay, so unlike the Wilcoxon Signed Test, which was in Lesson 1, the Wilcoxon Signed-Rank Test also takes into account the magnitude of the differences by summing over the ranks of the absolute differences. Here are the details. We have D1 through Dn, random sample of pairwise differences. We will sort the absolute value of the di's from least to greatest. We let capital Ri be the rank of the absolute value of the di's. Then our test statistic. We add up these ranks where the di was positive. So the question that comes up is, under the null hypothesis, what is the expected value of W? Well, let's think for a moment. The possible ranks. We have rank 1, rank 2, rank 3, rank 4, out to rank n. We have the di's range from 1 to n. So if you added up all of the ranks, not just the ones where di is positive, but all of them, well, you see we are adding up the first n integers. So I could write this as I equals 1 to n of I. There's a formula for this. It's n times n plus 1 divided by 2. The sum of the first n positive integers. Well, under the null hypothesis, we expect half the di's to be positive and say half to not be positive. So we would expect half of this to be the expected value of W. So the expected value of W is half this total sum. Another way to write that is n times n plus 1 divided by 4. This is our answer to this question. Well, we reject the null hypothesis when the observed test statistic is too far away from its expected value. How could you figure out, say, a null distribution for this W? One way would be to program it as a permutation test. Another way is that R has this pre-programmed as Wilcox.test. And the distribution of the test statistic W is derived using a normal approximation for a large sample size n, and the exact distribution is used for a small sample size. That would be using this function in R. Okay, fantastic. Next, I'd like to talk about the two-sample Wilcoxon Rank-Sum Test. This is the unpaired. So in this case, we have x1 through xn, random sample, y1 through ym, random sample, but the sizes are different. So n and m are different numbers. We may not use a paired test. In fact, we can't really make the DIs because n and m have different sizes. However, we can still test this null hypothesis. The probability that x minus y is positive equals 1/2 versus, and here is our two-sided alternative at least, the probability that x minus y is positive is not equal to 1/2. For the Wilcoxon Rank-Sum Test, we rank all of these data values together, x1 through xn and y1 through ym, under the null. We think of the x's and the y's coming from the same distribution. Now, let's get into the test statistic. So you notice I have this red bolded note. The literature varies as to which test statistic is used in the Wilcoxon Rank-Sum Test. So I'm going to talk about two common definitions of the test statistic, and then for us, we'll focus on the way that R does it, as R is the language we're using the whole semester. So one of the definitions would be you just add up all the ranks that come from the x's. In words, we sum the ranks of the random sample x1 to xn. Well, what would be the expected value of this test statistic? Okay, let's think for a moment. Unlike in the signed-rank test, we're not ranking n numbers. We're ranking n plus m numbers. So the possible ranks are 1 through n plus m. Okay, so let's back up and just copy and paste this. If we add all the ranks, we would have a sum I equals 1 to n plus m of I. And using our formula for the sum of the first, in this case, n plus m positive integers, we get n plus m times n plus m plus 1 divided by 2. Well, you see, what would we expect if we just add up the ranks coming from random sample x1 through xn? We would not just multiply this by 1/2 because you see this and this have different sizes. Let's think about proportions though. We would expect n over n plus m, this proportion of this sum, to come from the x's, and we would expect m over n plus m, this proportion of this sum to come from the y's. This is under H0, of course. Now add them up, you see these add up to 1, which is wonderful. So let me erase this one. We are summing over the x's. So the expected value of this statistic would be this, which simplifies because n plus m divided by n plus m is 1, we get n times n plus m plus 1 over 2. So this is the expected value for this test statistic. All right. This is one of the common definitions for the Wilcoxon Rank-Sum Test statistic. However, the one used in R is the one we will discuss next, and this is the one we'll focus on since our programming this semester is in R. So here, I will call this one W. We add up all the ranks coming from the x's and then subtract off n times n plus 1 over 2. Let's think about this for a moment. So in words, I can keep this. Minus, well, n times n plus 1 over 2. This is the sum from I equals 1 to n of I, the sum of the first n positive integers. It would be if x1 through xn are the n smallest values out of all of this. So minus the minimum possible value. Now, our test statistic has expected value. Well, if you think about this, we have this previous random variable, and then we're subtracting off. This is a constant. So we can take this expected value. This goes back to our discussion of linear transformation of random variables. Oh, how beautiful is this? So the expected value of W is this minus here. Now we can simplify this sum. Maybe let me add a blank page just to simplify this, and then we will put our final answer. So just in my numerator, you notice that I can factor out an n, and then I have n plus m plus 1 minus n minus 1. Okay. One last step to simplify this. Here, this one, this one, this one, this one, it all adds to 0. And so I'm left with n times m divided by 2. So this is our expected value of the test statistic W that is used in R. Let's write it. Just like with the Wilcoxon Signed-Rank Test, we reject H0 when the observed test statistic is too far away from this expected value. In R, we can also use Wilcox.test for the Wilcoxon Rank-Sum Test. Now, I'd like to do an example just to illustrate the concepts on the last 2 pages. So at this point, let's switch to R. The data we will work with in this example comes from this tooth growth data, which is built into R. There are actually 60 observations in this data, but we are going to use just part of it, really to illustrate these 2 different test statistics, and then we will see what R does by calling Wilcox.test. Vector X has 6 tooth links, vector Y has 8 tooth links. In vector X, all of those guinea pigs received 1 milligram vitamin C per day. In vector Y, all of those guinea pigs received 2 milligrams vitamin C per day. Now, here I'm going to have vector R, which is ranking all of the X's combined with all of the Y's. If you want to see what R looks like, it's here. So the first 6 of these are these 6. These are the ranks coming from vector X. These are the ranks coming from vector Y. You can see all together we have 6 plus 8, which is 14 ranks, and our ranks are the numbers 1 through 14. Okay, very nice. Now, this first statistic, I would just sum over the ranks of the X's, and we have 24. On the other hand, the second statistic, which I call W, we take that number and subtract the minimum possible, which would be, in this case, just adding up the numbers 1 through 6. We could also call Wilcox.test. In order to run the rank-sum test, we use paired equals false. If we wanted the signed rank test, well, we would need X and Y to have the same length, but then we would select paired equals true. You notice here the W, the W is 3, which agrees with this second statistic. All right. Well, let me just forward through this example. This is what we just calculated, noticing that the test statistic R is reporting with the Wilcox.test is this one. Okay, great. I will end this video with a little more discussion of permutation tests. So in lesson 1, we used R to program a permutation test version of the Wilcoxon Signed Test. In this lesson, we programmed the Wilcoxon Signed-Rank Test and also Rank-Sum Tests as permutation tests. The null distribution of the test statistic is obtained by evaluating the test statistic on each permutation of the data. For this reason, the codes for the different permutation tests look very similar. But I want to make a comment about one of the steps. So recall last time, permutation tests have 2 steps. First, we create permuted or rearranged or shuffled data sets using symmetry under the null hypothesis. And then we calculate the test statistic on each of the permuted data sets. A few comments on one. For paired data, we permute within each pair. That's what we saw in the last lesson, and that's what we will see in the signed rank test. This is in order to keep the paired structure of the data. However, for unpaired data, we permute the entire data set. The type of permutation in general to use is decided based on the model assumption. Other permutation tests could use different types of permutations in this step 1. Step 2 looks very similar for all permutation tests. And if you change the test statistic, you get all kinds of different tests. Now, in reality, we don't need a permutation test for the Wilcoxon Signed-Rank Test or the Wilcoxon Rank-Sum Test. We could just use the R command. However, for advanced statistical tests, the theoretical null distribution may not be available. In those cases, this is when permutation tests shine. They are very practical and very straightforward tests, and this is why we're learning how to program them in R. So thank you so much, class. At this point, you can work through some of the R commands in Canvas. Thank you.